Hey everyone, so this is our second of three videos for solving systems of linear equations. In the first one we looked at graphing, and like I said in that video, graphing is limited, that if it had really large, the solution, the values for that were really large, that would be hard to graph. Likewise, if they're really small or a fraction, again, reading that off a graph isn't very practical. So these next two methods are definitely more applicable in more situations. The idea of a substitution is where we're going to isolate one variable and then substitute one equation into the other. So this first one I have here is probably about as straightforward as we can have. This one's y equals something, and this is y equals something else. And what that means is I can take this, since y equals x plus 14, I can drop it right there for that y. And then I'll have an equation that's just some x's. I can solve for x and then plug back in to get my y value. So let me show you what that'll look like. Making the substitution, I'm going to have x plus 14 equals negative 2x minus 6. And let's add the two x's over to this side, so it's linear, so I'm getting x's to one side and numbers to the other. So this would be 3x plus 14 equals negative 16. Let's subtract that 14 over, and we get 3x minus 14 on both sides. That'd be a minus 30. And then dividing both sides by 3, we have x equals negative 10. So we got the x coordinate of our solution, but remember when we were solving these before, what we're looking for is the point where the lines are crossing. So I know the x value, but now I have to plug that back into either of these two equations and use that to get the y value. So this equation looks easier, so I picked that one. Negative 10 plus 14, and it looks like y equals 4. So my solution set for this one would be 10 and positive 4. Before I get that back there, before I go ahead and do this next example, let me take a second and explain the inconsistent and dependent solutions and how they're going to look in this section and the next section. So for what I just had here, we had y equals one thing, y equals the other. I'm going to set a couple up like that and just kind of, and actually I think we just did them in the last video. Let me scroll up there for a second. Oh yeah, these two examples work great. I will just use those. So let's say I now set these equal to each other. And this is from the 5.1 video. So I'll do a substitution here. So plug that in, and I have negative 1/3 x plus 2 equals negative 1/3 x minus 1. So if I add this 1/3 x over, I'm going to get 2 equals negative 1, which is false, and I could keep solving and get, 3 equals 0. But as soon as I get that false statement, that's where, actually I think it was back here, I was saying we'll get 0 equals a number, or two numbers that aren't equal to each other, and that's how we're going to be able to tell that that one, the lines are parallel. And this we can look at the equations and know, but often that's not the case. So this is how we'll run into it in these next two sections. Likewise here, you can see if I set, this is the one that came up dependent in the last video because they're identical equations. And if I set those equal, oops, if I actually set them equal, I subtract the 3x over and I get negative 3 equals negative 3, so I get this true statement. If I kept going and added the 3 over, I would get 0 equals 0. And so that's how we know it's going to be infinite, is when we get a true statement like this where all the x's drop out. When we get a false statement, that's the kind that's going to be D and E. So we'll see that in 5.2 and 5.3 as well, just algebraically. This next example, number 7, it is not, so this was nice because it was already solved for y. For this one I need to do just one step to get one of these variables by itself, and that x right there is definitely the easiest thing to isolate, so that's the move I would make. So I'm going to bring this 6y over and just say negative 6y plus 29 equals x. And now that I have that, I can take this and plug it into the other equation right there. So that's going to look like -7 and then times -6y plus 29. And then that's going to be -6y equals -23. And so there's the substitution. And then we'll clean this up a bit. And we go -7 times -6, and that's going to be a 42y. And then -7 times 29 came out to, oops, forgot the y there, -203. And then -6y equals -23. Before I start moving stuff around, let me collect like terms. So 42 minus 6 should be 36y minus 203, keep forgetting that y, equals -23. I'll add that 203 over, and now I have 36y equals, that is 180. And then dividing both sides by 36, and I get y equals 5. Once I have that, I can back solve into either of these equations. I'm just going to put it in this one right here. I could put it anywhere, but that one looks easy. So x plus 6 times 5 equals 29. So that'd be x plus 30 equals 29. So subtracting, and I get x equals -1. So solution set for that one is going to be -1 and +5. Let's see, so for this, that y is almost by itself, but I would have a lot of fractions if I divided that 3 out, so I don't think I want to go that way. This looks a little bit easier right here, so if I add that 4x over to this side, then I'll have y equals 4x minus 2, and that seems like it would be easier, so just write that out right up here. Y equals 4x minus 2. And now, since this y is by itself, I can plug that chunk in right there for that y. So that will look like 3 times 4x minus 2 equals -8 plus 12x. And then we just clean this up and see where it goes. So 3 times 4 would be 12x. 3 times -2 will give me a -6 right there, equals -8 plus 12x. And then when I go to solve this, this is where you know something, it's going to be one of those two kind of weird cases, because when I subtract that 12x over to get my x's to one side, they all drop out, and then I'm left with -6 equals -8. So that is a false statement, and so what that means is those lines are parallel, so this one is a DNE or inconsistent. Again, I think for the computer wants DNE. And then this last one, same thing, we're always just trying to figure out which is the easiest variable to get by itself, and that x right there definitely looks like the way to go. So I'll add the 4y over and get 4y minus 15. And now that will let me put that right there, oops, for that x. So -16y equals -60 minus 4, and then 4y minus 15 is the substitution for the x. And then again, we just clean this up and see where it takes us. So -60. Give me a -16y right there, and minus and minus will make a +60. So -60 plus 60, those drop out. And then you can see, as soon as you're right here and you can see both sides are going to kind of come out the same, you brought that over, you would get 0 equals 0. That's the kind where it has infinite solutions. And again, for the computer, I think it wants an infinity or dependent if you're writing out the word name for it. So that's kind of what there is to substitution. Substitution is a pretty good method. Sometimes it is harder to get the variables by themselves than with these problems, and then that's when the next method, and then also these ones only have x and y. They can have as many variables as you want. wanted, so we could have 4 equations with 4 unknowns, and then substitution would be actually kind of a terrible way to solve that. And so the last method we'll look at in the next video, which is elimination or addition, it goes by both names, that's kind of the one that generalizes to most cases. But substitution is good when, if you have something like that where the variable's already y equals and y equals, this is definitely the easiest way to solve it, or when something is easy to get to isolate a single variable. Cool, so we'll come back and we'll look at one more version of solving these.